Hello, everyone. Everyone's already asking about the midterm, so let's talk about that super quick. Actually, let's cover what we're talking about today, and then we'll talk about the midterm at the end. So let's wrap up the stuff with lists and things, and then we'll talk about the midterm afterwards. And we can review some stuff as needed. So we're not going to do again in the aims of being not too fast. We're going to do some simple stuff. So we're just going to talk about types, which is what we've been using all along, but we're just going to remind you a little bit about it. So we talked about we needed types for quantifiers. We've needed types before when we in the assignments. Every time we talk about an order, we mentioned types. So let's just quickly review what those are, and then we'll move on. Right? All right, sounds good? All right, great. So for example, when we talked about an order, the thing we said for orders was, we said an order relation is from a type tau to a type tau to a type booleans, right? Okay, so that means because the first two are the same, I can't have a number and then a letter. They have to be the same kind of thing. So when I write x is less than or equal to y, x and y have to be the same type, right? Likewise, we said equality at the very beginning was of type tau to booleans, okay? So you can never compare apples to oranges. That's what the types ensure, right? That's when we write the first argument is of type tau, and the second argument is of type tau. They have to have the same type, and the result is a boolean. Okay, so just quickly go over this idea because we're going to add on a new type. Right? So if you recall, we had yesterday we talked quickly about the type sequences. Right? Sequences of elements of type tau. Right. For example, people in a line from city tau. Okay, and now today we're going to talk about a new thing called set of tau. This is just having a bag of things of type tau and running around with them. Okay, so for example, what's a good example? A swimming pool with people from city tau. Okay, so these are our new examples for today. So we've and we'll just talk about their differences briefly. If you're not comfortable with anything, please let me know. Okay. So I'll just quickly go over types just to remind you of what's going on. We talked about types showed up at the very beginning when we talked about equality. Okay. Then we saw them in the assignments when we talked about O plus and when we talked about ordering, and then again in A3 when we talk about division. Right. So types not terribly new. So we've seen function types before. Yesterday we talked about sequence types. We've already met the booleans, the integers, and the naturals. There's a few continuous types that we're not really going to look into. And today we're going to look at sets. Okay. So we've been using the colon all along to denote typing declarations. True is of type boolean, k is of type natural, and we can put them right in the middle if we want to. Right? So this is all covered in chapter 8.1 of the book. And many languages let you do this. For example, when there's overloading and there's constants and you want to specify the constant belongs to a particular kind of type, you can annotate the type. Languages like Haskell, for example, let you have annotations right in the middle like this. Right? So this is a very useful programming language feature to say, hey, this is the type of the thing, or if you want to cast the type or change the type, okay, to be able to express typing annotations right in the middle of expressions. Okay. So The book uses typing notation with times. We'll get to what times means at the end. So until we get to what this times means, this idea of forming products or Cartesian products, what we're going to do until we get then is we're going to use this arrow notation, which is what we've been using all along. So we've avoided using product by instead using these arrows, right? So we have a plus operation, and we write underscores for where the arguments go. And the first argument has the first type, the second argument has the second type, and then the result is the final type. Okay. And of course, just as we had expressions before, now we have to have typing rules for expressions because we've added typing into our system. And so just as before, so we've mentioned this one before. Sorry, here it is. Where did I go? I went too far right here. So if we have a function from t to r, and we have an expression of type a of type t, then the result of applying the function to a is going to be the type of the result r. Okay. So again, the first few are the arguments, then the last one is the result. Okay. This means that before, when we could write some expressions, now they're not type correct. So before, some students would write, a true plus 1. So that was a common error some students made at the beginning. And CalCheck would tell you this is a type error. And the reason is because true is a Boolean, 42 is a number, and minus is a operation that takes two numbers. Okay, so type errors are very useful in programming. You don't want to accidentally try to add apples to oranges, right? It doesn't make sense to say, hey, I have a color and I have a number and I'm going to multiply them. What does it mean to multiply a color by a number, right? So the usefulness of typed expressions is to avoid these silly little mistakes that we might write accidentally. Okay, so very useful in programming languages. Okay. So the function application in the book is usually with a small dot, but many modern programming languages will use this kind of notation, g of z. What we've been doing so far is we've been avoiding the parentheses just because they're not pretty. So you are welcome to write, h of z equals g of z, or without any parentheses. So we prefer without any parentheses just because it's more elegant. It's easier to read. There's the half semicircle in fixed notation doesn't really give you that much. So hopefully that's, again, nothing new yet. And we've talked about modus ponens before numerous times. So if you recall, modus ponens says if I have P and I have P implies Q, then I have Q. Okay, that's exactly what function application says. If I have P and I have P implies Q, then I have Q. Okay, the idea that that F is a witness of this proposition A implies B, and X is a proof that A is true, means that I have a proof that B is true, which is F of X. So recall at the very beginning we talked about how functions really are constructive propositions, right? So a type is like a proposition, and then a value of that type is like a proof of that proposition, right? So this is the so-called Curry-Howard correspondence that we've talked about a few times. And I think we've sketched it out a few times over here. Modus ponens. So the relationship we've alluded to it a number of times, and we might not get to talking about it in full detail, but it is a very useful thing that programming and proving are really the same sides, are just different sides of the same coin, right? Programming and proving. Alrighty. So now we're going to get to these new expressions for sets. Okay. So the other day we talked about having cons for sequences. Sets, most people have seen them already, just as most people have seen addition and subtraction. But we're just going to again look at them from a different angle. So if you have a value of type tau, then a value of type set tau is a collection of elements, right? It's like having a bag of things and running around with them, right? So what does that mean in particular? So let me point out some neato things, right? So here, the position or order of people matters. Okay. Here it does not. The order does not matter, right? Okay. If I have people standing in a line, then who's the first person, who's the second person matters, right? But if I have people in a swimming pool, I don't really, like, there's no order. They're not standing in a line, right? Their position doesn't matter. They're just swimming around. So that's the first difference, okay? So in particular, here we have 1, 2, 3. So this list is not equal to 3, 2, 1. But for sets, we would write 1, 2, 3. Notice we're using curly brackets now. And with curly brackets, we can change the order around. Right? So we'll use square brackets for sequences, curly brackets for sets. Okay. And sets are useful just like sequences. And again, it's what you use them for that determines their usefulness. If you have a queue of people applying for things, you might want to use a sequence because the order matters. If you just have a bunch of people for an activity or a bunch of applications and the order doesn't matter, you might use a set. Okay. So now we're getting into data structures, right? And data structures programming, right? So that's where we're getting into now, right? So just as with sequences, we won't spend too much time on sets. Just want to flesh out the basic syntax so that way they're easy to use, and we'll defer some of the stuff to the exercises. And we'll see by the end of the lecture that sets are really boring in comparison to sequences because we've already seen sets. Spoilers, sets are just propositions. So everything here is just syntactic sugar for propositions again. All right, so it's like people on different sides of the world, and they're like, oh wait, it's the same thing. So that's why sets aren't that interesting. And there's some arguments by some academics that say, you know what, why even bother with sets when you can just work with propositions? They're the same thing. But it's important for you to see them because you will likely encounter both sets and propositions in your future university career. Okay, dokes. Another cool thing about sets is we get to practice more with orders. So we talked about this abstract square less than or equal to order. And then yesterday we talked about prefix and subsegments for lists. We have similar stuff for sets. And just as we talked about meets and joins, intersections, max and min, unions. So likewise, we have them for sets. Okay, so all of that abstract theory we've been developing in the assignments now immediately applies to set theory. And so many of the theorems you saw in assignment 2 are now going to be immediately applicable. And the proofs you did in assignment 2 will immediately apply right here. You don't even have to reprove them if you don't need to. But we're going to show just the basics of sets, so that way you could prove them using just set theory without using order theory, if you were so inclined. Okay, dokes. Yeah. So we talked about membership of sequences yesterday. Membership of sets is also a thing because they're both collections. So you can ask if something is inside a collection. Okay. So let's quickly talk about the notation. So let me get back here for a sec. Here is an example. Oh, sorry. I have my example right here somewhere. Here it is. So here's an example from when we talked about quantifiers, right? Recall when we have a concrete expression, we can express it more formally using a quantification. Okay. The whole point of the ... notation is to be able to use a quantification. And so likewise, when you see a set expression, E0 to En minus 1, that's really just the set of all x such that this constraint happens, right? X is either E0 or ... X is e to the n minus 1. And of course, to avoid the ... what we say is this expression f is inside the set of all expressions E where X satisfies R, means, remember the OR notation, ... with OR is exists, right? So this is just exists right here. That is, there exists some X satisfying R such that F is equal to E, okay? Are there any questions? Okay. So this is the main distinction, and then the fact that order doesn't matter is because with the operation or, the order doesn't matter with or. Okay. So let me point that out just in case. Why? Because when you say x cons y cons x, this does not equal y cons x cons x. But down here, when you say x equals E0 or x equals E1, this is the same thing as x equals E1 or x equals E0. Okay. So there, just to make that again clear, there is no, it's not an and, it's an or right here. So there's ors, and this is with cons. So the order doesn't matter. The order matters for cons, but it does not matter here. So when x is not equal to y, of course. Okay. Alrighty. Okay. All right. So this is really the main new thing. So unlike lists, which were just another inductively defined data type, sets are defined using propositionals, right? They're defined using existential quantifiers, right? And so they inherit all the properties of the existential quantifier, right? So for example, we'll use this to be empty when you have empty right here, so R is false, then you get empty range. And what's empty range? Empty range for existence is just the unit of OR, which is false. Okay, so a lot of the properties of the predicate logic are inherited. In particular, notice all the operations we talk about for sets are defined in terms of predicates. Okay, so let's just go over them briefly. Two collections are the same precisely when for every x, for every element, the element is inside one precisely when it's inside the other, right? If I have two swimming pools and I'm like, are these the same swimming pools I'm looking at? I just need to look for every person. Is Sally in here? Yep, she's in both. Tommy? Yep. Yeah, Bob? Yep, they're both, okay, so they're the same swimming pools because I don't really care about the order of people in there, right? If I have some people in the swimming pool, are they contained in a bigger collection? Easy, just look at the first collection and everyone in the smaller one is going to be in the bigger one. All right. So is there a question? All right, so here, it's a good idea. So this notation, to be clear, x with R spot E, it can be read as the collection, right, or set of E where x satisfies R. Okay, so for example, x with even x, right? So is the even integers, and x with 0 is less than or equal to x spot to c dot x is the even non-negative integers, and x with 0 less than or equal to just x slash spot to c dot x is the collection set having just 0. Okay, so here's a few examples of these. All right, so multiple bullets, not great, but hopefully that helps. Okay, all right, great. So I just wanted to wrap this up before we moved on. And again, because the ordering on sets is defined in terms of implication, right? The ordering on sets is defined in terms of a universal and implication. Sets are a good place to get extra practice on working with quantifiers. But the properties of sets, as you can see right here, are defined in terms of the properties of the propositional calculus. So that it will be really easy to prove properties here, and hopefully it won't be any difficult for anyone to really work here, because the difficulty is in the propositional calculus, which we have covered already a while now. Okay. So this idea is called a set comprehension, and this is how sets are written down. Okay, so when we write down this concrete syntax with ... notation, we really mean a set comprehension. And then, of course, to avoid the ... dots, we can simply use an existence. Right? We can use a full existence like that. Right? So here's a simple example. Recall we're going to use this abbreviation, right? So we've had these abbreviations for quantifiers before, and we can treat set comprehension like a quantifier. So we say x bar r, right, or x satisfying the requirement r to mean all the x that satisfy r, right? And if we don't want to say f is an x that satisfies r, what we're saying is just r with x becomes f. Okay, so it's a very nifty little theorem and just shows that it's not really that much new stuff. So f is in the set of things x that satisfy r, right? If and only if r with x becomes f is true. Okay, so not a deep result, right? But it's nice that we can actually prove it. Right? Like that. There you go. Mm-hmm. Okay. Please do ask questions, or if you're concerned about things. All right. So we're using the same quantifier notation, right? And so many of the quantifier rules continue to hold. So for example, here I had a 1-point rule, and we're going to call it a 1-point comprehension, right? Just to make it easier. But notice the curly braces stay on the outside, right? The empty comprehension, okay? So many of the rules can be adapted again for a sets. Okay, ducks. So we're not going to cover sets too much because of the fact that sets can be defined in terms of predicates. So this is what the idea is right here. If I have a collection S, well, a collection S is just all the X that are in that collection. Okay. And if I say X is inside the collection of things X that satisfy R, so X is a solution to R. Oh, so I'm just saying R holds, right? With X everywhere already in there, right? So it's this duality that makes sets not new. They're really just predicates, but packaged up. Okay, so that's the idea here. Sets are packaged up predicates. Okay, So the properties of predicates you expect with the disjunction are just called sets, right? And then lists are just packaged and ordered, like the positioning matters, right? And then there's ones where the ordering doesn't matter. So there's different ones, the so-called boom hierarchy. So maybe we'll cover more of it if we have time in the rest of the term. But sets and sequences are the most popular branches of the boom hierarchy. There's also trees, bunches, strings. What else is there? Those are the other popular ones: trees, bunches, and strings. So we might mention some others as we go along. Anyhow, so this is the main theorem that we get by identifying sets with predicates. Is to show two sets are the same, it suffices to show that these two propositions are the same. Okay, so two sets are the same precisely when for every element they have the same elements. That's what it means for two sets to be the same. They have the same elements. But recall with theorem 916, which says when there's a for all statement, you can drop the for all. And so we get two sets are the same precisely when this proposition is the same. Okay, so now we're getting even closer to the fact that, hey, sets are kind of propositions. Okay, and we can use this to prove properties about sets as well. So I'll get to some calc check code in a moment. All right. Just checking. All right. So notebook has already been posted for working with sets. I think it will be due Thursday next week, and you can use almost the same stuff you used as before. The only new thing is now there's extra curly brackets everywhere to deal with the fact that we are ignoring order. This is the main idea. Order does not matter, right? As well as multiplicity. So in this theorem, we're showing multiplicity doesn't matter too, right? If you have two things, that's the same as having one thing, okay? So this is like saying I want to have a representative from the city. I don't need to have at least one, right? So in here we're saying a swimming pool with people from city T. So instead of people, we can say with representatives, right? So I want one person. If there's multiple people representing the city, I don't care. How many are from Hamilton? There's one person from Hamilton, good enough. Multiple people from Hamilton, it doesn't matter. How many from Mississauga? How many from Toronto? So order doesn't matter, and neither does multiplicity. Okay. So if there's two representatives from a city, that might as well as one representative. Right? I don't care. Okay. So when you do care about multiplicity, that's another structure in the Bloom hierarchy called bags, and a bag is completely different. Okay, and we might not get to those. They are covered in the book as well. So bags and trees are covered in the book, but we might not get to them. Okay, dokes. Another useful operation on sets is how many there are in a set, how many elements. If I have a pool with people swimming in it, how many people are in the pool, right? Homework 14 is on sequences, and sequences will not be on the midterm. So good question. But let's get back to the midterm at the very end. So I just want to wrap up right here with sets. Okay. So the hashtag is just to count how many things are in a set. And you will likely see this as you go on in your university career. Some fields of computing, some places in mathematics prefer that you work with sets instead of working with propositions. So sometimes you'll be like, oh, we're doing everything with sets, and the professor might prefer that, or the field of study just might be better tuned to working with packaged up collections instead of working with propositions. And the reason that it might be better tuned for that is sets, because they're really packaged up propositions, they abstract away quantifiers. So let's so let me just make that up. The packaging is that they hide the use of quantifiers such as for all exists via equality or set 2. exists vs in and slash sum and slash sum via hashtag. Okay, so all these quantifiers, for all goes away by using equality or inclusion. Existence goes away by using membership. Summation goes away by using count. So a bunch of quantifiers suddenly disappear. So sometimes when people want to talk about for all and exists and they don't want to talk to you about for all exists, they'll just use sets. Okay, so that's another power usefulness of sets. Okay. Finally, before we're done with the basics of sets, there's the idea of a power set, which is the power set of S is all the things that are parts of S. So all the smaller pieces. That's all it is. So the Booleans, there's true and false. There's also, so the Booleans are true and false, but there's also just true. There's also just false, and then there's also nothing. Okay. So it's like considering the collection of sub-segments of a list, but when the order doesn't matter, instead of having subsegments, you have subsets. Okay, so it's not, again. Someone is asking about right here, 1112. Yeah, so we're just saying hashtag S means look at all X that are in S and then add 1 for each possibility. Okay, so for example, if S was the collection true false, then there would be X would be true and X would be false, and for each one I add 1, and so hashtag of the Booleans for true and false would be just 2. There are 2 Booleans. Okay. Yeah, it's just a counter. Excellent. Finally, in introductory math classes and sometimes in philosophy classes, when people talk about sets, they like to get fancy and say there's a universe of discourse or a domain of discourse, right? And that means I don't want to tell you, I don't really want to make it clear what T is when I talk about it, so I'll just call it my universe. Okay, so, and sometimes it's denoted by a capital U, all right? So for example, all my sets are contained in the universe. This is like the infinity or the top element, right? Just as every proposition proves true, every set is contained in the universe. Okay, so just as we have P implies true, we have every set is contained. Oh. Nope, the other way around. Every set is contained in the universe. Okay. Universe. Okay. Or if you like, X is less than or equal to positive infinity. All right. So that's and again, this is from assignment 2. So a lot of the stuff here for sets is really again already done in assignment 2 and in propositional and predicate calculus. So there's the changes in perspective. This idea of packaging is the new feature, but otherwise nothing else, right? So let me try to elaborate on this slightly more. So for example, if I say P is from the natural numbers to the Booleans, and I say P of n is equal to n equals 1, or n is or n, sorry, let me say n is even and n is less than or equal to 5. Okay, so this is a proposition, right? This is a predicate. Okay, but if I say here is a collection of all the n type natural numbers with n is even and n is less than or equal to 5, right? This is the collection of numbers that are 0, 2, and 4. Okay. Notice that the collection is all solutions, things that make P true. Right? So the predicate P, when is it true? All these are the solutions of it. So the set just keeps track of where is P true, and then P is just a predicate that just returns true or false when you give it an argument. It checks is that argument even and less than 5, right? So this is the nature of the relationship. When you package them, you say, hey, let me keep track of all the small pieces, whereas the other one is not. So for example, for implementation purposes, you might want to have this one because it's just 0 to 4, which is much smaller, whereas this is infinite, right? You can ask, what is P at 99? P at 99 is going to be false because 99 is not less than or equal to 5. So that's a different duality, but that's the idea behind them being packaged up versus not. Okay, I can represent P using this collection of 3 elements, or I can represent P as this expression. Okay, so different ways to see the same thing. Okay, and so this is what we wanted to get to. Meta theorem 11.2.5 is wrapping up this idea that they are the same. To prove a theorem about sets, you just identify the union, the disjunction as the join from assignment 2, the intersection with conjunction or the meet of assignment 2. The universe is like true or the top element from assignment 2. The empty set or false is like the bottom element from assignment 2. And then there's a negation and complement, which we haven't introduced into the setting of abstract orders. But this is what we've been leading up to with assignment 2. This structure is called a lattice, a complemented lattice, right? When you have joins and meets with bottom and top values, this is a bounded lattice, and then you can add complements on top. So all the theorems over here are also theorems of over here because they're all theorems of the lattice, right? And so that's what we're trying to do. We're trying to get the complemented distributive linearly ordered lattices, right? So these are words we've used before, linearly ordered, right? So, and that's the nice thing about this theorem. It just says, hey, this is another instance of that. So recall how we had a lot of instances for this ordering. There's less than or equal to, divisibility, implication, now subset, right? But if you prove theorems using just square less than or equal to, then those theorems apply everywhere else. So this is an interface, okay? So that's the nice thing here. So the key feature here is they are both instances of the lattice, square less than or equal to, meet, join, interface, okay? So you can have this interface, and then you can have multiple implementations, and sets and propositions are both instances of this interface. So that means all the stuff that was true before is true now. So golden rule, it will work. Excluded middle, it will work. Identity of disjunction, it will work, right? So all the theorems you learned before are not new. So just, and this is why I wanted to point out to the fact that it's an interface. You don't have to worry about learning a lot of new theorems. There's the few definitions, like what does hashtag mean, right? What does inclusion mean? But then the rest is it's all in the interface, okay? Which you've already met in assignment 2, and which you've been practicing with using propositional logic all along. So that's the thing about using a common interface. The theory of sets, the theory of propositions, the theory of orders all fall into the same interface. So less theorems to remember, right? So that's neat. So here's some of the, sometimes depending on other books you read, these are called free theorems or theorems from the interface, the lattices. So here's absorption. That's nice. Here's distributivity. Here is weakening. Right? All these theorems you've seen before are now just packaged up into the language of sets. So somebody just said, I thought it was sufficiently funny, I'll point out to it. Jeevan says, looks like I'm all set. Thanks. Yeah. So there's a few more I would like to talk about, like what this product is, but maybe I'll stop right here and just talk about the midterm that's coming up. As I mentioned yesterday, sequences are not new. They're just induction, right? But a list carries information. It's like a natural number that carries extra information. It's tagged with information from tau. And then we said, oh, what if we don't care about the order of sequences? Then we get sets. And then we realized, wait a minute, sets are just propositions from a different point of view, right? If I change my perspective, I just get predicates again. Right. So even though sequences are not new, just in order to be fair and not to force too much on you, we won't have sequences on the midterm. So I just want to let you know, sequences will not be on the midterm, even though they're not new. So sequences will likely be on the next midterm, midterm 5. Likewise, sets are not new, but just to avoid stressing everyone out, sets will also not be on the next midterm, okay? So sets and sequences will likely show up on midterm 5. But hopefully by then you will have had sufficient exposure and comfort trying them out that it won't be a concern. To see this idea that sets are not new, you really do need to prove some of these theorems, and you're like, wait a minute, I proved this theorem using just properties of the order. I didn't even need to invoke anything about sets. I just used the fact that this less than or equal to operation is an ordering. It's reflexive, transitive, and symmetric. Oh, so all I have to do is prove that it has these 3 properties, and then I can suddenly prove all of this, which I did back in assignment 2, because all I need is the order interface, right? So as long as you prove the axioms of the order interface, then everything else becomes a free theorem. So that's very handy. Sets and sequences will not be on the midterm. So I do want to point that out. There was an assignment here for you. Here it is, residuals. So this assignment definitely has some content that will appear on the midterm. Not all of it. Again, we don't want to stress you out or cause anyone to be worried. So some content will be on midterm 4, and I've written down which it is. If it's too long for you, you can just go down. So here's more stuff from assignment 2, just to show you how useful this is, and we really are going to use this kind of stuff maybe next week or the week after. So where is it? Right here. So this kind of sentence stuff, I told you last week, hey, I showed it to you in slides, and I said I'm gonna probably test you on this, and I'm like, oh, maybe I should give them more exercises to test them on this. So here's a bunch of exercises. Here's the thing. Look, this part is the same. This part is the same. This part is almost the same except for one tiny operator. Golly, if only they were instances of the same interface, if they satisfied the same properties, if you can drive a Honda, you can drive a Jeep because they both have a car interface. Doesn't really matter which kind of vehicle it is. They have a steering wheel, they have brakes, they have turn signal. You know how to work with the interface. So it doesn't matter which particular car you're working with. Likewise, some of these theorems really, really easy to prove. Okay, ducks. So I hope that helps you feel a bit better. Of course, you do need to know how. You do need to know stuff from previous midterms. So, for example, you need to know how quantifiers work. you need to know like 1-point rule, empty range, nesting, dummy renaming, whatever. To avoid having to remember so many of these, I've in the abridged lecture notes, I've given you generic forms using O+. And so there's no rules for all or exist here because they all show up in terms of these generic rules, right? So like here's 918 and other theorems that show up using this generic setting, right? So 9.5 and 921, a lot of them can show up by using a generic phrasing. But if you're not comfortable with the generic phrasing, of course, the slides have the concrete instances, which I also repeat here, in terms of sigmas and for alls and exists. So here's 5 theorems, and these 5 theorems all follow from this one formulation, this one theorem. So it's consult as you see fit. Some people work better with abstractions like O+, other people do not. So please consult the book and the slides and make use of the course help. Okay, dokes. So someone asked which exercises or notebooks. I'm not going to make a list because I feel like last time it was too daunting for people, and to make the homework prep was too daunting. So this, please consult assignment 3. Please consult assignment 3, and be comfortable with the quantifiers. So for example, I think it was assignment homework 12 on summation quantifiers, for all quantifiers, existence quantifiers. So know the quantifier rules. Look at assignment 3. Definitely be able to use with and. Okay, so these things we talked about from before. Let me just show you briefly in case you've forgotten. So you definitely need to know how to do using. You need to know how to do for any, but you need to be able to use the keywords with. Okay, so you need to be able to say, hey, here's a thing with another thing. Okay, so this stuff that we've looked at before. So X with Y with Z. So nested widths. So you do need to know how to do that. It was on midterm 3. So that's a thing you should definitely know. So for any, you definitely need to know how to do for any. You should be able to use the relaxed proof style, assuming, using. Please do use the online course help forum. Please share any tips or tricks you have on the new channel for study tips and strategies. If you're like, this worked for me, maybe let other people know, and that will be useful for them. And I wish you all the best, and please ask many questions on Teams, and I wish you all the best. Yeah, take care. I'm here. Do you have a question?